Alright, so good morning students. Today we will talk about a system of continuous degrees of variables or continuous degrees of freedom, and this will be a system under canonical ensemble. So, the case study would be that of an ideal gas where the degrees of freedom are continuous random variables. So, I am going to take the case study of classical ideal gas. We had taken this case study of the ideal gas under constant energy conditions, that was the micro canonical ensemble. So, today I am going to take the same gas where particles are to be treated ideally in the sense that they do not have any interaction potential. So, a microstate typically of a classical ideal gas is composed of a set of coordinates and momenta. This constitutes a single microstate mu, and the microstate belongs to our macrostate NVT. Okay. So, this is your microstate, and there are a large number of microstates, and this is our macrostate, the specified value of NVT. Okay. So, now you can think of this ideal gas as a system which is enclosed in a container, and your particular particle here is having momenta pi, and the location is some qi, and so on and so forth. Okay. So, this is a box of volume V, there are n particles in the box and it is in contact with a heat reservoir at temperature T, which means I can write down the probability density function. Remember, we do not have probabilities here because the degrees of freedom are continuous. So, we need a continuous version of our probabilities, which is a density function. Now, this is to be realized as a function which, when integrated over the entire volume of phase space accessible to my system, is unity. Okay. So, I can define my PDF of a particular microstate, which means the microstate here is nothing but a particular set of values for momentum and positions, which keeps continuously changing. So, this is one microstate, and I want to know its probability density. So, this would be 1 upon h to the power 3 n into 1 upon n factorial e to the power minus beta times the Hamiltonian of the microstate over the canonical partition function. Now, as you can see here, what is meant by the probability density function is that I can ask myself what is the probability now of finding our system, in the neighborhood of so, if I basically ask you a question that the neighborhood of some in the neighborhood of some part of phase space. So, some value of q and p in the phase space of some point now this is momentum and this is you know then basically what is meant by here is that I would like to write this some of the phase space point as some point in the phase space let us call that point in the phase space as some point as mu naught, which is given by some specified values of all the particles. Okay. So, all qi's are specified and all pi's are specified, and the neighborhood of this point mu naught means that in the vicinity of mu naught, and that is basically number of states between some mu naught and mu naught plus d mu naught, okay, and that probability is given as simply p of mu d of mu at mu equals to mu naught. Okay. So, that is the meaning of probability density. So, you go to your 6n dimensional phase space and so this is basically 3n momentum coordinates and I have 3n position coordinates in this 6n dimensional phase space. If I isolate a point as mu naught, some microstate, and if I want to ask what is the probability of finding a system in a small shell of volume, in a small shell around this mu naught, then basically of volume okay. So, in some sense this would be like in the neighborhood of this mu naught, and so this would be like some distance d mu naught. So, you construct a volume around this mu naught, then your answer is this probability that I have written here. Okay. So, let us from the definition of this probability density function or PDF, compute the partition function. So, if you look at the definition of the PDF, you can think of the canonical partition function simply as a normalization of your PDF. So, I can write down the canonical partition function, which is the norm of this PDF. So, this partition function by the definition of p of mu that I have taken is simply the norm of this. So, which is nothing but partition function normalizes our PDF. So, it is simply by this definition given as 1 upon h to the power 3 n into 1 upon n factorial into these n dimensional 3n dimensional position integrals to conserve the space. So, I will use the space down below to write it down. This is the cell volume h to the power 3 n. The n factorial here reminds us that we are looking at a case of ideal gas where particles are all identical. So, to avoid overcounting of the microstates, because particles are indistinguishable, there are precisely n factorial microstates for each arrangement of n particles. So, I need to divide the partition function by n factorial to avoid the overcounting, and then I have these integrals over the entire phase space. So, I am going to write down d cube q 1 into d cube q 2 all the way to d cube q n. Then I have these momentum integrals of the our Boltzmann factor, which is e raised to minus beta. The Hamiltonian of a microstate is nothing but summation over all particle momenta, where I will go from 1 to n pi square by 2 m. Okay. So, pi square is nothing but the sum of squares of momentum of each particle, and there are n particles in the system. So, straight away I can see that the position integrals and the volume integrals are independent. So, I can integrate them separately. So, the position integrals will give me each position integral will give me, so I can write down this as integral d cube q 1, and since each one of them is separate, I can say that this is nothing but to the power n. I will take just one of them and raise it to the power n, because they are all the same and they are independent. The same applies for the momentum integrals. So, let me just write them after a small manipulation here. So, I am going to write down this as integral d cube p 1 into d cube p 2 all the way to d cube p n into e raised to minus p 1 square by 2 m. Correct. So, now I can write this simplify this further. I can write this as 1 upon h to the power 3 n into 1 by n factorial. The single volume integral would give me v, but I have raised it to the power n. So, it gives me v to the power n, and look at the momentum integrals, since they all these pi's are independent of each other. So, I can write this as a single integral over one particle and raise this to the power n. Okay, since all these particle momentas are independent. You can basically write that momentum and positions are independent. Now, you can write this as so the momentum integral that I have written is if you look at p 1 square is the sum of squares of the components of momentum of the first particle. Okay. So, this can be written as I can write down this as d cube p 1 can be written as triple integral dpx, dpy and dpz of e raised to minus beta px square plus py square plus pz square of the first particle, okay, and I can raise the entire thing to n. Okay. So, I am going to write down this as for the first particle itself. So, a single particle contribution has to be raised to power n, that will give you the contribution coming from n particles. Now, you can see that each component of the momentum of any particle is independent of the other component, which means I can write this as further simplification is possible here. I can write this as simply integral dpx e raised to minus beta px square by 2m, but now I have to raise it to power 3, there was already a power n sitting outside. Okay. Since px, py and pz are independent. That is the definition of a vector, its components are linearly independent. So, then I know that now the integral that is sitting inside the bracket is a simple Gaussian integral, which is just square root of pi by a being the prefactor of px square. So, I can write this as v to the power n square root of pi by a being the prefactor of px square. So, I just have a beta here and 2 pi m, but this entire thing is raised to the power 3 n by 2. So, I am going to the entire thing is raised to 3 n. So, I am going to write this as just 1/2 that comes from the Gaussian integral and 3 n which was already sitting outside. Okay. So, this is the canonical partition function, and let us just simplify it a little bit. So, what I can do is I can write down this v raised to n upon n factorial and take the h inside this parenthesis. So, I can write this as 2 pi m upon beta h square raised to 3 n by 2. Okay. So, this is my canonical partition function, and I can write it as v raised to n upon n factorial. Beta is just 1 upon k t. So, I can write this as 2 pi m k b t upon h square to the power 3 n by 2. Now, 2 pi m k t upon h square is related to a length scale. Why do I say it? Because partition function is dimensionless. It has to be, you are going to take a logarithm of this to compute free energy and build a bridge that connects to the thermodynamics. Very soon I am going to construct that bridge, but let us know that, let us be aware of the fact that Z is dimensionless, which means I have got a volume to the power n already. N factorial is dimensionless, which means this guy, if I write it like v to the power n upon n factorial into 2 pi m k t upon h square raised to half raised to n. So, this quantity should have the dimensions of v to the power minus 1, because there is a v raised to n as a prefactor. So, unless this 2 pi m k t upon h square square root,
the whole race is 3n, right? So,
right,
the should be 3 by 2.
right. So, this has to be So, I am going to write it as so the entire 2 pi m kt upon h square to the power 3 by 2 should have the dimensions of 1 upon volume, because then raised to the power n it has the dimensions of 1 upon volume to the power n. Okay. So, that will cancel with the dimensionally it will cancel with the dimensions of v raised to n. Now, which tells me that since volume is constructed as a cube of a length scale, I have to take this tells us that the entire thing that I have indicated as v raised to minus 1 is a cube of a length scale. So, I can tell that 2 pi m k b t upon h square raised to just the 1 half is related to some length to the power minus 1, because now if I raise both to the power 3 that becomes lambda to the power minus 3, which is like a 1 upon volume, that is what I want. Okay. So, if I call this as some 1 upon length scale, okay, some inverse length scale, and I am going to tell you that this is an important length scale. So, let us this gives, let us work out what it gives. My lambda as simply h upon square root of 2 pi m k b t. Now, this length scale very clearly it goes to 0 as the temperature goes to infinity, and this length scale becomes larger and larger as the temperature goes to 0. So, this is a very important length scale which goes by the name of de Broglie scale length. It sort of manifests the onset of quantum mechanics at low temperature. So, one has to associate lambda, that at what temperatures one has to consider quantum mechanical effects. Naturally, lambda alone will not tell us the onset of quantum mechanics. You have to compare lambda with some other length scale. So, let me give you some comparison. So, if you have a density, so there would be a length scale that you can construct from density. So, I would say that there is a construct some no, I am going to tell you how quantum mechanics sort of how can you tell that quantum mechanic effects are arising in your system. So, construct some length scale from density, which is something like a material property of a system, because density is, once you decide the density for your system, it remains as it is. Okay. So, n particles in a box of volume V fixes your density. Now, you can play with your temperature and hence play with your de Broglie wavelength and see how does your de Broglie wavelength compare with your density length scale. So, let us say you have a density which is fixed. Okay. So, construct some density length scale lambda sub n, which is nothing but n to the power minus 1 by 3 roughly. If you take an inverse cube root of density, it will give you a length scale, which is I am going to call as a density length scale. Now, the ratio of your de Broglie wavelength over lambda n decides if quantum mechanical effects are present. So, if lambda is over lambda n becomes a number which is much smaller than 1, you know that lambda n is dominating here, which means your density scale lengths are much larger compared to your de Broglie wavelengths. So, you will not be using quantum mechanics here at all. When will lambda by lambda n become much smaller than 1? Well, certainly when your either your density is very so lambda by lambda lambda over lambda n to the power n simply tells me that this is the classical limit where your lambda is much larger than lambda n. So, your density is fixed to some length scale. Now, if your de Broglie wavelength is much smaller, which means your temperature is too high, that is the high temperature limit. So, your quantum mechanical effects are almost gone.
Depending on this length scale, can you say anything about distinguishability or distinguishability and indistinguishability? Because if we say the length scale, we can talk about the.
So, distinguishability is embedded in quantum mechanics from the property of the wave functions itself. So, for example, we know that fermions and bosons have wave functions that are either antisymmetric or symmetric, depending upon whether they are Fermi wave functions or wave functions for bosons. So, indistinguishability is embedded in quantum mechanics from the beginning, and so we do not have to introduce n factorial in the calculations. That is a totally separate argument from whether you are in classical limit or quantum limit. So, every system can be pushed to a quantum limit by increasing density or reducing temperature. Both have the same effect. See, if I increase the temperature density, my length scale lambda n reduces. So, let me write down first. So, the other limit of course is when you are in much larger than 1, and I am going to say that this is the quantum limit. Now, let us see both the cases. See, you have in your hand two things, temperature and density. If you take high temperature and low density, high temperature would make your lambda smaller, de Broglie wavelength smaller. So, your numerator in the first case is getting smaller, and the fact that you have taken low density will push your lambda n to larger values. Your particles are now separated farther and farther because you are at low density. So, numerator is smaller, denominator is larger. What does this ratio become? Numerator is smaller, denominator is large.
It's very small.
Numerator is small, denominator is large, the ratio becomes much smaller. Okay. So, that is your classical limit. Now, the quantum limit for the system can come if you go to high density and low temperature, which means if you go at low temperature, your de Broglie wavelength will inflate, it will become larger and larger because it goes as 1 upon square root T. So, low temperature means de Broglie wavelength will go up. So, look at your expression. So, de Broglie wavelength is going to larger and larger values because the temperature is taken to lower and lower values. What happens to the denominator?
Where density is very small.
When density is small, now the particles are basically closer to, when the density is large, not small. So, the classical limit is high T and low density, and the quantum limit is sitting at, I am going to use a different color. And this is sitting at low temperature and high density. Now, think, the numerator, which is lambda, depends on temperature. So, if you go to low temperature, what happens to the numerator?
That increases the value.
Yeah, and if you go to high density, what happens to the denominator?
Decreases.
So, what happens to the ratio?
Greater than.
Yeah, because 10 by 100 is definitely much larger than 100 by 1, which is much larger than 1000 by 0.1, and so on and so forth. So, you are making this ratio larger and larger. So, the de Broglie wavelength that I have written here, it tells us the onset of quantum mechanics if you have another length scale to compare. So, I have argued here that the length scale to compare is the density length scale. Okay, you cannot just say by looking at high temperature and say that classical effects are expected. No, you have to also look at density, because that will give you another length scale, the density length scale, with which you can compare and tell whether classical effects are seen or quantum effects are seen. Okay. So, you need a reference, density scale length being the reference in the scales. Okay. So, your system can go to the appropriate limit depending upon whether, depending upon the ratio of this length scale. Okay. So, the ratio is important. Now, let us get back to our calculation. So, we have reached a stage where the partition function is ready for use, and as I have always been telling that the partition function exists for a certain purpose, it helps us to establish a connection with thermodynamics. So, let us make that connection. So, the partition function in the canonical ensemble was given as okay. Fine. So, now I am going to build a connection to thermodynamics. And the starting point is the computation of free energy. So, the connection from classical mechanics, classical statistical mechanics to thermodynamics is obtained by connecting the microscopic world, that is residing in your logarithm of z, to the macroscopic world which is in free energy. These are thermodynamically averaged quantities. So, they represent macro states or macro state information. So, now I can write down my free energy as simply minus kT, and logarithm of z would simply give me n log v. These are natural logs, okay, to the base e, and since n factorial is large, I am going to use a Stirling's approximation here. So, it is minus n ln n plus n, and the parenthesis as 3 n by 2 ln 2 pi m kT over h square. And so, you can sort of simplify it for for the sake of convenience. So, you can pull out the number of particles and write it as minus n kT, and the first two logarithms can be written as logarithm v by n, and you have a 1 here when you pull out an n. So, you get a 1 here, that is ln e to the base e. So, I am going to club that e here, okay, and this is simply 3 by 2 ln 2 pi m kBT over h square. Okay. fine. So, let me just write it slightly. Okay. Now, so let us call this as expression 1. So, you recall from thermodynamics that your free energy is given as E minus T s. Okay. So, you can easily write it in differential form, and this simply becomes okay. And from first law you can write d minus T d s as minus P d v plus mu d n. So, if you recall the first law of thermodynamics, we can write down the heat given to a system as work done by the system minus mu d n, and there is also change in internal energy. So, you can write down plus d E. Okay. So, if you write down d E minus T d s, it is minus P d v plus mu d n. Now, I can use this to get an expression for entropy. So, the entropy here is nothing but the partial derivative of free energy with respect to temperature at constant n and V conditions, constant n V conditions. So, my entropy is nothing but minus dF over dt at constant n V conditions, constant number of particles and constant volume. I can also write this as d by dt of minus f at constant n V conditions. Okay. Now, your expression for f is here, equation 1. Okay. So, this is your free energy f, fine, which is obtained by taking logarithm of the partition function. So, you can take the derivative of free energy or minus f as you take it, there are two terms. So, if you take the derivative of the first term, what you get is just n k b, okay, and you write down the entire term, which is ln E v by n plus 3 by 2 ln 2 pi m k b t over h square. Now, you take the first term, which is just n k b t, and take the derivative of the second. Now, ln E v upon n has no temperature in it. So, from the second term you get 3 by 2 as a prefactor, then 1 upon the argument of the log, which is h square by 2 pi m k b t, and you have to take the derivative of the argument with respect to temperature, that will give you another 2 pi m k b over h square. A lot of things are going to cancel off here. So, you can knock off the h square with x square, you can knock off 2 pi m k b with 2 pi m k b here, and you can knock off this temperature T with this temperature T. Okay. So, just 3 by 2 n k b is remaining there, which is particularly eye pleasing because it can give you the internal energy of a gas at constant n v t conditions, as we shall see. So, this is nothing but 2 pi m kBT over h square plus 3 by 2 n k, because everything else got cancelled. Let us call this as expression 2. So, we now have an equation for the entropy of an ideal gas. From this you can construct a lot of other things, and as you can already see that the entropy here is extensive in nature, thanks to the fact that we have taken care of the indistinguishability. So, if I scale n v by lambda n and lambda v, my entropy scales by lambda times s. So, it is purely extensive, and it is also a monotonically increasing function of temperature as expected. And what I am going to do here now is basically compute the pressure of a ideal gas. Okay. So, from the ideal gas equation of state, I already know that pressure is equal to nkt upon volume, or PV equals to nkt. But can we derive it here? You have derived this in the case of kinetic theory of gases, okay, using the approach of kinetic theory. But using the statistical mechanics approach, you can get the equation of state for an ideal gas. That is very simple. Just look at this equation that I have written here for the incremental change in free energy. This equation. So, if I look at the incremental change in free energy, I can write down the pressure as negative derivative of free energy with respect to volume at constant n in t. Okay. So, I am going to use this equation to my advantage and compute the equation of state. So, I am going to write down for pressure I am going to write it as negative derivative of free energy with respect to volume at constant NT conditions, number of particles and constant temperature, which is nothing but derivative with respect to volume of minus f at NT conditions, constant N and constant T conditions. Now, if you look at the expression for Helmholtz free energy, you can see that only the first term in the square parenthesis has a volume dependence. The second term does not have that dependence. Okay. So, what I am going to do is just take the product of nkt into ln EV by n as the free energy term that will give me. So, if you take the derivative of free energy with respect to in this expression with respect to volume, so what you will get is just nkt because I need derivative of with respect to volume of minus f. So, just nkt that is the prefactor, it is volume independent here. Okay. And ln EV by n simply gives me n by EV, that is the 1 upon argument of the log, and if you go and see the prefactor of so if you see the argument, it is EV by n. So, it will give me EV, one more EV, and 1 by n's derivative with respect to so yeah, with respect to volume, right. So, it is just E by n. Absolutely right. So, you can see that this is nothing but, so you can see that this E knocks off and this n will knock off. So, what you will have is just nkt over V. Okay. So, this will equation of state of an ideal gas. Okay. So, now you can also compute internal energy of an ideal gas. So, that the fact that you have computed pressure and entropy, you can also compute what is the internal energy of the ideal gas. Now, there are two ways to compute internal energy. So, one is the one way, which is the easier way, is to basically use the thermodynamic law that connects free energy with internal energy. So, I am talking about basically from here. Okay. So, you can write down the internal energy as F plus T s. Okay. And for F I can substitute the entire expression. Just going to copy it. So, this is the expression for the free energy F So, this is just the expression for free energy, and I need to take the expression for T s. So, let us copy the expression for S. So, this is the expression for S. So, we were supposed to add T s. So, I am going to add T s here. So, as you can see, the first term clearly knocks off with the first term in the second parenthesis. So, this term will knock off with this term, because the prefactor is just nkt in both the terms, and very easily you can see that this term will also knock off with this term. And what you are left with just 3 by 2 nkt. Yeah. So, here I need to multiply a t here, because this is T s. So, therefore, I can write down E as 3 by 2 nkbt. So, this is another important result that goes by the in the context of the ideal gas. This is the internal energy of the ideal gas. We have already obtained the equation of state, which is P v equals to nkt. We have also obtained the entropy, and the free energy was already obtained to build the connection with the thermodynamics. Now, what you can also obtain is if you look at the incremental free energy, you can also obtain chemical potential of an ideal gas at under NVT conditions. So, if you look at this relationship, you can write down for mu as dF by dN at constant volume and temperature. Okay. So, you can take the derivative of free energy with respect to n at constant volume and temperature, and that will give you mu. So, from thermodynamics, dF by dN at constant volume and temperature should give me the chemical potential. Okay. So, you can compute the chemical potential as if you look at the function free energy. So, let us copy the free energy so that we can use it readily. So, this is the free energy functional formula. I think this is already there as F plus Ts. So, if you are going to use it, so this is already in front of me. So, this quantity is F. Let me copy it anyway. So,
how do we justify the variation of free energy with number of particles?
yeah, in fact, all other, not just here, that is a good question. So, let me just finish this computation, hold on to your question for a second, and so this is my free energy expression. So, you recall that your free energy is basically this expression, okay. And from here, if I want to compute the chemical potential, I have to take the derivative with respect to n at constant V and T. Let us do that first. So, again you can see here that so I am going to do it. So, let me take the first term, which is n minus n k T, and the derivative of log E v by n is nothing but n by E v, okay, into E v, and this will be minus 1 by n square, and that is it. Second term does not have any n, plus ln E v by n plus 3 half ln 2 pi m k b t upon h square into minus k t. So, if you see, you can knock off this E v with this E, 1 n with this n square, and so what you have is nothing but minus just k t. So, I can take k t from this common, okay, you just have k t here, because this entire n square will cancel. There is an n square, no, 1 upon n square, right? So, this n square will cancel, there is 1 n here and there is 1 n here, okay, and minus becomes positive. So, if I take k t outside, then I have 1 minus logarithm of, if I take these two logarithms are combined, what do I get? I get E v upon n into 2 pi m k b t to the power divided by h square to the power 3 half, fine, by clubbing the two logs, and the minus k t is coming with a minus sign here because I have taken k t outside. One more step, I can write down this 1 as ln E, okay. So, this is like k t, I can visualize this 1 as ln E to the base E. So, it will simply become let me write it as ln E to the base E minus ln E v by n into 2 pi m k b t by h square to the power 3 half. This is the end of the logarithm, this is the end of the square bracket, fine. Maybe one more step and we are we have reached our goal, which is ln. So, I do not need a bracket anymore because now these two logs will be combined to 1. So, this becomes just n by v into h square by 2 pi m k b t the whole raised to 3 by 2, fine. Fine. Now, you can think of this n by v as some density, n by v as some density, and h square by 2 m k t, the whole square root is nothing but our d by wavelength or d by scale factor. This entire thing is raised to the power 3. Okay. So, now you can see in some sense the role of chemical potential here. There are two length scales coming, one is the d by length scale and the other is the density length scale n, and that is whose logarithm decides the chemical potential in our case. So, let me write down the three results what we have obtained here. So, we obtained the chemical potential, we obtained the internal energy, and we obtained the equation of state for the ideal gas. Now, let me write down the differential form of first law and tell you the meaning of it. I am going to copy this, and this is important. So, the entire derivations of the meaning of these thermodynamic derivatives. Which derivatives? These derivatives. So, let me sort of push it on the right side because I need some space. So, this is our this basically provided us with a tool to construct all these derivatives. So, we constructed, for example, for pressure we said that it is minus dF over dV at constant n and t, and the same thermodynamic law gave us the expression for entropy as minus dF over dt at constant V and n, and the same chemical potential gives us the expression as dF over dN at constant V and t. Now, the question is, I have computed these three quantities, pressure, entropy and chemical potential, by taking a derivative with respect to V, derivative with respect to temperature and derivative with respect to n. But in my canonical ensemble, these are the three quantities preserved or conserved. A macro state is specified by the triplet NVT, and I am taking derivative with respect to NV and T. So, what does that mean? Well, it simply means that you have to construct canonical ensemble at different values of V, keeping n and T constant, and simply tell how free energy changes with volume. That will give you the pressure of that system. What does that mean? For pressure, for example, so for computation of pressure, I am going to take the first case only, and that will that should be enough to explain how entropy and mu can be computed. So, you create different canonical ensembles. So, let us say you create this ensemble at n, t and volume V 1. Okay. This is one system, call it as the system S 1. You take another canonical ensemble, this time you do an experiment with another canonical ensemble. So, let me sort of make the system in contact with the heat reservoir. So, this is in contact with some heat reservoir. It is exchanging energy and this system is maintained at n, t and V 1 or you want to call it as n V 1 t. So, the volume of this system is V 1, we are taking n particles at volume V 1 and temperature T. Okay. Call this as system 1. Then you do an experiment with another system. This time this new system is in contact with another reservoir, but at the same temperature. The number of particles are same, but the volume of the system is V 2. This is my second system. Okay. You took you are free to choose any volume. So, you chose the volume V 2, number of particles and temperature are kept the same. This way you constructed large numbers of systems varying only in volume with respect to each other, but number of particles and temperature are taken to be constant. Now, from all these systems, let me call let me show the nth system also. The nth system is also connected to a reservoir, temperature T, we have the same number of particles, the volume of this system is taken as V n, some value I do not know. And now from all these n systems you basically construct, you compute their free energy versus volume. So, this would be like something like this. So, this is your V 1 and this was the free energy of the first system. This was the volume of the second system and that is the free energy of the second system, and so on. This way you simply extend it, and somewhere down the line you have the volume of the nth system, and correspondingly you have its free energy. You have simply done a bookkeeping of this and you call this as Fn, and in the end you are just opening your book and plotting these values, fine. And I am saying that the pressure of system 1 is nothing but the slope here, which is dF by dV. The pressure of the system at V 2 is nothing but the slope here, and the pressure of the system nth system is nothing but the slope here. The slopes here are nothing but dF over dV, which is what I have shown here, negative of that slope. Similarly, you can construct systems at various temperatures keeping n and V the same, and after you have constructed a large number of such systems varying by small temperatures. You compute you plot F versus T and take the derivatives at the value of temperature you want to take, and that would give you the entropy of the system, fine. So, that is the meaning of these derivatives. So, do not be alarmed when you see the derivatives, they have a simple meaning. So, I am going to call this as simply this derivative as simply dF by dV at V 1, which is giving me minus pressure, fine. Okay, so we break here, and when we meet again we will discuss the Gibbs canonical ensemble, which is an ensemble that is constructed by allowing one more thermodynamic variable to fluctuate, which is either volume or magnetization. So, if you allow a volume to fluctuate, you can control pressure. So, for an ideal gas this will lead to an NPT ensemble. For a magnet in contact with a magnetic field, in presence of a magnetic field, this would also be a NBT ensemble. So, we will discuss the Gibbs ensemble in the next lecture. Thank you.